just so I wouldn't get confused. I could have also used subscripts. Whatever you want to do is fine, but just be clear so you can figure out what you're doing on your exam so the grader knows what you're doing. If if you have a problem, this is probably pretty elaborate. Suppose you had a problem with 5 objects, right? You're all tied together. Oh gosh, awful. You can have fun actually. So anyway, so suppose you had some awful thing like this, and there's all these different angles, and oh, it's awful. Oh no, which way to go? Whatever the problem is. So in that case, what I might choose to do is have separate axes in all these different cases, right? Just to make my life easy. And what I would do for each of these, right, is without any different axes, maybe I wouldn't use X, Y, Z, all the rest of the letters in the alphabet. Maybe I would just have X and Y in every case, but label them. It's X1, Y1, X2, Y2. Or this is object 1, 2, 3. This is sort of useless advice in a way, because you're not going to have 5 objects tied together tonight. But anyway, that's one way to handle a situation like that. Yeah. Right. Car going in a circle on a flat track. Well, what do you think? Which way would the force of static friction point in that case? Absolutely. If you're on ice and there were no friction, you can't go in a circle, right? You're just going to keep going straight. Your car can spin around, but you can't. Your center of mass is going to go straight. I can say that from personal experience. But if you make a left turn and you're on pavement and you've got rubber tires, right, and it really works, in that case, yeah, the acceleration of the car is towards the center circle. And the normal force isn't going to help you. Well, I should be careful how I phrase that. It will help you in that it's related to the force of friction. You need a big enough normal force to provide enough friction, right? Because of the static friction. Is it less than or greater than or equal to mu static times normal force? It's less than. That's right. You can't have arbitrarily large force of static friction, right? Otherwise, you could park a car on a essentially vertical incline and decide half down park your car. You can't do that, right? So that's because there's a limit to how high it can go, and the limit is based on the normal force. So in that sense, normal force helps you, but it doesn't help you in the sense that if it's not banked, it's not helping you, and that there's no component to the normal force that can point to the center circle. You need friction to keep you going in a circle in that case. The work the road does on the car. Right. So I'll ask the assembled crowd. So how much work is done by the road on the car if the guy never, or whoever's driving, never skids? Zero. Because the road. So if the road's not moving with respect to your coordinate system, so if you're holding still, right, and the problem's all described in terms of whatever the racetrack frame, right, and the car's going around. Doesn't matter what direction the car's going, whatever. As long as there's no skidding, as long as it's all static friction, no kinetic friction, no work is being done on the car due to friction because the force is exerted on a part of the car that's not moving. In fact, it's the only part of the car that's not moving. It's the bottom of the wheel, right? That's the only part of each of the wheels. Yeah. So no work is done. Yeah. What do you think? More questions? Yes. What the velocity is at the top. So if you have a car going around a loop and it's going around right here. So in terms of the direction of the velocity, it's got to be lined up with the track. So which way? So right here, for this, when this guy's coming around, right here, which way is his velocity? Yeah, straight that way. It's parallel to the track. It is part of the track, tangent to the track. That's right. Which means the magnitude of it or the direction of it? The magnitude of it. Well, how would I calculate that? If I know I start from rest right here and I let go, of course when I'm ready for it, it doesn't do that. Anyway, so it goes around. How would what's the fastest way for me to calculate that if I'm given the initial location is, depending on what the radius is? Yeah, conservation of energy. I'd say 1/2 mv squared, which is 0 initially, plus mgh, which is if this is h, right, equals 1/2 mv squared over here, which is non-zero. He's moving now, so I get a non-zero. Plus mg, whatever 2r, whatever h is, right? So that's how I'd probably calculate it if I have enough information. If there's friction in the problem, suppose I've got a car that's going down this friction. Well, now I have this external work term that ruins it for me a little bit, unless I know what that. Well, actually, suppose I have so let's think about this. Suppose I have a block that sits up here, and I let it go, and there's friction, there's kinetic friction, and it's sliding, and it slides around, right? Well, in that case, it's not the case that the initial gravitational potential energy minus, or let's just say the difference in heights. It's not the case that I can just take the difference in these heights, right? Call that h, and say mgh. Mgh does not equal 1/2 mv squared. 1/2 mv squared for velocity here is going to be less than that. But can I calculate if I know the length of this path, and I know how long it is to get from here to here, right? It's 2 pi r over 2. It's just pi times r. It's the arc length of half of the circle of radius r. And then this is a quarter of an r, or whatever it is, less than a quarter. But let's say I know from the problem description what the path length is along here. Could I calculate how much work is done by kinetic friction? Yeah, actually, I think I can. Even though it's speeding up and slowing down. Why is that? Because friction, kinetic friction, doesn't depend on the speed. So even if you had friction in the problem, you could still do it using conservation of energy, but you'd have to remember to include a non-zero work external term, right? And would it be positive or negative, that work external term? Negative, because the kinetic friction took away some of the energy, right? In other words, 1/2 mv squared at the bottom would be, well, at the lower location, right? At the final location, would be less than it would have been otherwise, right? Yeah. Yeah, sure. Let's do that real quick. Did I answer your question? I see. So that's related to what you're asking. So let's do that real quick. If you have a vertical circle and you have to figure out what's going on, what do you do? Here, is this good? I'll do it right here. So if you've got some circular track and there's you're right. Let's say you're right here. So you're at some angle below the horizontal or whatever. All right. So I'd say okay, let's define my x-axis that way, and I can define my y-axis that way. And I can call this tangential center point, whatever it is. Right? And I'd say okay, here's my object, whatever it is. Maybe it's sliding, it's a ball, whatever it is. Well, let's do this with no friction or with friction. No friction. So if there's no friction, I'll put the wheels on here. All right. There's no friction. I'd say well, the normal force we know points that way, right? So I think a free body diagram. Right. I got my force normal. I got my what else? Force gravity. Are there any other forces in the problem? If there's no friction, no wind resistance, no friction, no springs, right? Nobody on the track pushing on the thing. So yeah, that's all there is. So then when I try to figure out what the acceleration is of this guy. Oh yeah. Points. I just lost a point right there. Oh yeah. Oh yeah. However, it's the discretion of the grader. So if you make some stupid error like I just did, but then you proceed and everything looks right, the grader may decide, okay, that's a typo. But if you make a mistake like that and then there's all kinds of weirdness, right? It's just not right. You can lose points for it. There's nonlinear effects that happen, right? Because the grader's trying to assess. All the grader's trying to figure out is one thing: how does this student know what she's doing or not, right? And so they have to make judgment calls about that kind of stuff. You know, different people have different handwriting and don't make it. Although I'd say you're better off to be as clear as you can be. Clear, and simplify things. Do everything you can to make it easy for graders to see what you're doing. Confusion costs you, right? If you can't figure out what you're trying to do, even if it's right, you lose a point. So yeah, a mistake like that can cost you a point for sure. Like I would normally take a point off that. That's not a normal force, it's a random force. But if some graders would give you the benefit of the doubt and not take a point off if they can see later on that you know exactly what you're doing and it was just a typo. But they have to, you know, it's a judgment call. It's tough. It's a tough thing. Grading exams hard. You think it's taking the test, I'm sure it is, but it's worse to grade them. If you don't believe me, if you don't want. But anyway, all right. So how do you figure out the acceleration? Well, what you do is you configure a diagram and now you choose your axes, as I've done. I chose actually to go down the slope. I could have gone the other way if I wanted. It doesn't matter. In fact, I could have also chose to go vertical and horizontal if I want. It's just that the equations are nastier or you have more terms in them because now this guy has non-zero. The normal force has non-zero. Actually, was that true? I guess it's not true. Yeah, it'll have the same number of parts, but it doesn't break down as nicely in terms of v squared over r. Like when you're trying to figure out what the acceleration is, you have to, in other words, if you want to figure out what the acceleration is ultimately, we're going to be relating these forces to the acceleration due to gravity. Excuse me, due to the acceleration due to the fact that it's going in a circle. And we have a formula for that, v squared over r. So if I want to use that the most expedient way, I'll choose to make one of my two axes point directly in that direction. Otherwise, I have to break that up into two components. I can do it. It's just a pain, right? So usually I choose these axes. And what happens next? All right. Well, let's see. Newton's second law. It's always where I go next. So the 3-by diagram, Newton's second law. And let's do it in the x direction. And then I get, and it's the same thing you've seen it 100 times. You just say, all right, in the x direction, I've got no component from normal force, right? But I do have a component from FG. What is that? It's FG times, is it sine or cosine? Well, let's see. Here's my FG. I'll make a separate diagram of this. Separate diagram. So I don't get so involved with this thing I get confused about. I like to have separate pictures for these things. All right, I want to have, let's see, a steep guy here and a shallow guy there. So this is the x component over here, and that's the y component. This is FG. Oh, yeah, and the small angle is theta, right? This is theta. Does everyone see that? I can read it off because I chose a theta that was much less than 45 degrees, so it's easy to read it off. I'm drawing my picture. And also, this is my original vector. The right angle has to be on the opposite side of the triangle as the original vector. Got my theta. So then what's this? Cosine or sine? I agree. And what's this? It's going to be sine. It's one more left. FG. Sine, theta. And then, okay, great. So I've got FG. In fact, I might just skip to the chase instead of saying FG. I might say, oh, it's my mass times G, and that's times, which one do I want? For this, I want cosine. And is it positive or negative? This component of the force of gravity. Yeah, it's positive, mg cosine theta. And now what about the other, see what the forces are there. Oh, well, the normal force, what is the x component of the normal force? It's nothing. So this is exactly the same equation we would get, right? A sub x, right? The x component. This is exactly the same equation I would get, the mass canceling out as it always does, if I just had a ramp, right? In the x direction, because I chose these axes, it works out nicely that the normal force doesn't do anything. It doesn't show up in the x direction. There's no component in the x direction. So that means that this expression is the same one I would have gotten if I just had a skier on a slope, right? A slope of theta with, well, theta with the vertical, right? Same equation. And then the thing that's different is the y direction. What's different about the y direction is that now I've got, let's see, what do I have? I've got, well, the normal force, of course, normal. We don't know what that is yet. In fact, we're probably trying to solve for that. Because we actually do know what the acceleration is, provided we're told what. We have to know what the radius of the circle is. What else do we have to know? We have to know how fast the thing's moving, right? We have to know how fast it's going. So if we know he's got velocity or speed v right now, okay, great. So then we know what the acceleration has to be. So the normal force is not positive or negative given my choice of axes. Normal force can be positive or negative. Yeah, positive. Because this thing is the length of the vector, positive number. I'm going to leave it positive in front. Say, okay, and then I have one more piece of gravity. Is the y component of gravity positive or negative? Negative. Mg sine theta, right? And that equals may. Well, m's probably will, well, m's can cancel out there, but we're actually solving for this, so it depends on m, so okay, fine. And then what is a sub y? Oh, yeah, I can rewrite that as v squared over r, right? So if you think about it, say, wait a minute, how come we have to do this before with a ramp? Suppose I've got an object sliding down a ramp. Well, in that case, we actually do this. It's just that what is the radius of the circle that's fit to the ramp? If you have a straight ramp that's going down like this, and given my drawing, it's a pretty steep ramp, and the angle here is theta. What is the radius of this curve? Right. So how far away is the center of a circle that's got a curve that's totally flat right here? It's got to be infinitely far away. Infinitely far away. In other words, the radius of the circle that effectively corresponds to a straight line is infinity. So if you stick an infinity right here, you get v squared. No matter what v you've got, it's finite. And it's going to be finite because you can't go faster than the speed of light in this universe. Then this is going to be a number that's, well, 0. So this is equal to 0. And that's that's using exactly the same formula, but using the same, everything's the same, except we're talking about a roller coaster that's infinitely big so that you have a straight ramp locally. And that's when you've got a normal force that just exactly cancels out. That's when you get this thing equal to 0. That's just, the normal force is just equal to the normal component of gravity in its magnitude, but opposite direction. Why? Because all it's trying to do is keep you going inside the ramp, from falling straight down, it's making you stay on the ramp. But once you've got some curvature, there's extra acceleration there, right? Or extra force needed to cause the acceleration in the y direction. Anyway, so you've seen that stuff before, but maybe I just described it differently. I don't know. Yeah. Yes. Yeah. Okay, that's a great question. You're saying, oh, is it okay to reorient your 3-by diagram compared to the physical description of the problem, right? I wouldn't do that because I'd get confused if I rotate them around. I try to keep it really the same. If whatever you do, make it clear. So if you rotate it, you might want to make a little notation to the grader. Like I rotated my 3-by diagram relative to the other picture just because it's easier for me. Just so they know what you're doing. I was going to say, that's not vertical. You got gravity coming off at an angle. You're going to lose points, right? So make it clear to them you know what you're doing. I wouldn't do it, but yeah. This Ferris wheel problem is just, man. Yes. Yep. Well, so I missed something you asked. It's almost like a trick. You're going to, all this is like a trick question, all these things, right? But they're not intentional. That's just the nature of it. So you're saying it's a Ferris wheel problem. Now, this isn't the Ferris wheel problem. This is a roller coaster. So it's speeding up as it goes down the hill. Ferris wheels don't speed up and slow down unless they're letting people off or whatever. But when they're moving and no one's coming off or going on, then they go at a constant speed, right? So that means that the frame has to exert not just a normal force, it has to oppose gravity more effectively than that, not just in the normal direction, but also a little bit in the tangential direction. So for the Ferris wheel problem, right, i.e. for the uniform circular motion problem that happens to be a vertical circle, in that case, the resulting acceleration, like in this problem, there was an acceleration that went down as well as that way. So the net acceleration, I only got one color chalk. The resulting acceleration is like doing this, right? it's pointing a little bit below the center. But if you have a Ferris wheel, it's pointing right at the center. How does it do that? Well, the frame, as opposed to the track in this problem, the frame is exerting a force on the car that counters gravity and provides enough force in the direction toward the center so that you get acceleration directly toward the center. Right? So it's a different set of forces. Yeah. It has a tangential component to its force, unlike the normal force in a roller coaster. Yeah. So if this were a Ferris wheel problem, then the y, x, for the x, yes, that's what I'm saying. I'm saying that if you have uniform circular motion, you know the acceleration in the x direction, would be 0. And so you put 0 into that, and then you'd have g times cos the LT. Oh, well, but then of course you have another force in the problem, because in this problem we only had a normal force, so there was no other force except gravity that had an x component. But in the Ferris wheel problem, there's another. This brings up another issue in general too. In the Ferris wheel problem, you've got two components to the force on the as you've broken up x and y here from the frame. There's an x component and y component, neither are 0. So the one way you can solve that in a problem like this, like when you put down your free body diagram, you can choose to write each of the components separately, the x component and the y component of the force of the frame on the car. That's probably the way I would do it if I know that I'm going to use those x and y coordinates. And I'll tell the graders that's okay, even though there's really components of the same force in some sense. That's the way I would solve it. This is a bigger issue for what's going to happen in the next few weeks. We're going to be dealing with statics and rotations and stuff like that. You're going to have a lot of problems where you don't know the direction that the force is pointing in, right? Unlike friction, where you're pretty sure, like you know it's either up the slope or down the slope, right? You may not know which direction it's pointing, but at least you know that it's, up to a sign you know which way it's going, right? But you can have problems with statics that are pointing in any direction, just kind of like the Ferris wheel problem. So in that case, what I tend to do is break it up right off the bat into two components, x and y, once I decide what my axes are, and then plug them in appropriately everywhere. And anyway, that's how I usually do it. The alternative is to put in an angle. We're spending a lot of time on vertical circles, but yeah, there we go. Yes. No, but that's a different problem, though, right? Is that a vertical circle or a horizontal circle? Horizontal circle. What are we going to ask? I'm sorry. What two forces? So should we write out Newton's second law? For that? Yeah, let's do that. So suppose you've got this problem, and it's going in a circle. Some circle, R, that goes from where the car is to, I don't know where, that's a pretty tight circle, but whatever, go into a circle. So, okay, so Newton's second law, how do you apply this? Well, in the x direction, as I've described it, oh, I see, yeah. So if we had a problem where this thing's going in a horizontal circle, constant height circle, we can do this with these coordinates, but that means that the acceleration vector is going to have a component along x and a component along y. That's okay, but I might have chosen different axes if that's what the problem was at the outset. Because I think it'll turn out to be easier that way. But it doesn't matter, we can do it this way too. So if you do it this way, what I would say is, all right, well, along the x direction, what are the forces? Well, there's these three forces in the problem. I've got, let's see, there's minus force of friction. Even the way I drew it, we don't know which way it's pointing, but I'm going to stick to my convention. Once I draw it that way, I'm going to stick to it, right? So I go, okay, I got minus force of friction static. And the car's moving in this problem, but still static friction because the bottom of the wheel is not moving, right, relative to the ground. So I've got that. Now what else do I need? And I think I got the sign right. Yes, I did. How about the normal force? Is there any component along x, given the way I chose my axes, to the normal force? No, it's 0. Okay, I can leave that out. How about force of gravity? Is force of gravity a non-zero component in the x direction? Yes. Is it positive or negative? Positive. Some students say, wait, it's pointing down. Yeah, but I chose a downward pointing, or more down than up pointing x-axis. So it's positive. Mass of the car times 10 meters per second squared times what? Times, well, let's see, let's break it up. Here's my force of gravity, mg, and now I need I need this. Right angle goes opposite from the vector I'm breaking up into components. The x component is over here. This is my angle theta, right? Am I wrong? Oh, I'm wrong. In this problem, I use theta to be the bigger angle, and so that means that this is theta for this problem. Does everyone agree with that picture? It's really worth knowing how to get your triangle straight. This class is all about getting your triangle right way around. So that means that the x component, which is this component, it's going to be positive because it goes from the tail of the original vector toward, it's a positive one that way, x-axis that way. And it's mg times, what is it, sine of theta. Okay? So that means I need mg sine theta, right? So let's do the x here, we'll do the y next forward. Okay, great. So now there are my forces. But what about the acceleration? That's what you're asking. What about acceleration? Well, it's ma. In particular, it's m times a sub x, and we can rewrite that as m times, well, we know it has a magnitude v squared over r, where v is the current speed of the car, but we need a geometrical factor right here because we're only going to get the component of the acceleration that is pointing down the slope. What is that? Well, here's the acceleration vector. We know where it points. I sort of tipped you off. I should have asked you which way it's pointing. But this is a horizontal circle, right? That means that right here, the acceleration points that way. Do you agree? Keep me honest here. So that means that I'm going to break this up into x and y pieces. Well, there's a steep slope over here for the x part, and then here's the y part. Right angle goes on the opposite side of the original vector, right? So which is x? Is the left leg x or the right leg going to be x? Left. That's it right there. Where's theta? Well, let's see. It's the bigger of the two angles. It's got to be right there. I just read it off without doing anything fancy. But if I want to be fancy, what I would do is say, well, this is parallel with that, and that is parallel with that. So these are like alternate interior angles. I don't want to be fancy about it. But the main way I do it is I just make sure my drawing has an angle that's well away from 45. In this case, it's bigger than 45. So I don't think I made any mistakes here. Is that right, everybody? If that's true, that means that this is my x component, and I'd say, oh, it's equal to whatever the full vector length of A is, A, I'll call it, times cosine theta. Do you agree?